If you had to pick just one geologic process that gives you the most practical information about a landscape in the most places, the geologic process to pick would be rivers. Rivers influence the landscape in most parts of the earth. Moreover, rivers are capable of eroding and transporting a large amount of surface material in a short period of time. Finally, rivers create habitats for plants and animals, both of which also influence the landscape. That magnifies the impact of stream processes on the environment and the landscape even more. So in this lecture, we'll look at rivers, how they form, how they impact the landscape, how water and sediment move in a river. And we'll look at how too much water in rivers can create problems, such as destructive erosion. So we'll also look at flooding. First, let's talk about where rivers come from. Have you ever tried to follow a river or stream to where it begins? It's not an easy thing to do, even if it's just a small creek, although it is a good excuse for a hike. Where and how a river is formed has puzzled people for a long time. The ancient Greeks proposed that fresh water was purified from salty ocean water inside of mountains. The mountains were imagined as honeycombed or sponge-like, with the purified fresh water supposedly emanating from them to form rivers. They were wrong about the purification process and about the internal structure of mountains, but they were correct that river water comes in part from groundwater. But in the bigger picture, rivers come from rainwater. Of course, there's rain that has recently fallen, but there's also rain that fell long ago and has been flowing as groundwater until it makes its way into the river. That makes rivers part of the hydrologic cycle, which I mentioned in Lecture 1. This reminds us of a couple of important things. The first is that all water is connected. That means if anywhere along the way water is polluted, in the ground, on the land surface, or in the atmosphere, then eventually that pollutant will, unless remediated, make its way into the other components of the hydrologic cycle. It's a reminder how important vigilance is in protecting water. The other thing that's important to remember is that we have a closed system in terms of water. It's called the Earth's hydrosphere. The hydrosphere extends from approximately a half a mile deep in the ground up to the land surface, and then up into the atmosphere another 15 miles to the ozone layer. That's essentially it. Practically speaking, that's all the water we have, and essentially all the water we've had for a couple billion years. Occasionally, you'll see diagrams of the hydrologic cycle that also include volcanoes. A volcano is always producing steam. In fact, water is the gas most emitted by volcanoes. What that illustrates is that some water will make its way from greater depths back into the cycle via volcanic processes. However, the total volume of volcanic water emitted each year is very small compared to the entire hydrosphere. By the way, some textbooks refer to this as juvenile water because it seems new. But in reality, volcanic water is mostly seawater that's been stored for a long period of time. So it's just another very slow part of the hydrologic cycle. Now, the entire operation of the cycle runs essentially on solar power. When you look at the hydrologic cycle, essentially you can start anywhere. But we'll start in the ocean. Salt water is evaporated by solar energy. During the evaporation process, salt water is distilled to fresh water. Atmospheric water exists as water vapor, which eventually precipitates as rain or snow. If precipitation falls as snow, it is stored, either for a short while and it melts, or the snow is stored long-term in snowfields and glaciers. If precipitation falls as rain, it lands on the surface, infiltrates into the earth, or runs off as surface water. Rivers come from all three: the runoff of rain, the melting of snow and ice, and the flow of groundwater into river channels. To finish out the hydrologic cycle, rivers and groundwater both flow to the sea. Sometimes that water is stored in lakes. Sometimes water is evaporated from water on the land surface. And sometimes soil moisture is transpired back into the atmosphere. That's the hydrologic cycle. So rivers form from water that's part of the hydrologic cycle. That water is collected in an area of land called a river's drainage basin. This is an area of land that controls where water will flow in terms of specific river systems. Here we see the Mississippi Drainage Basin and its major rivers in pink. Drainage basins are separated by an imaginary line called a divide. This is a topographic separation of one drainage basin from another. In some cases, divides can be clearly recognized as a ridgetop of a mountainous area. For instance, you can see the Cascades in orange and the Sierra Nevada in teal dividing the drainages. Through process of stream erosion, the location of a divide can change, but usually that's a very slow process. In rare instances, headward erosion, stream erosion in its headwaters, can cut through a divide. When this happens, rivers on the opposite side of the divide will reverse flow into the eroding stream. That's called stream piracy. This happened in the Shenandoah River system in West Virginia and Virginia. Headward erosion by the Shenandoah River resulted in the piracy of the western portions of Gap Run and Goose Creek. A large-scale divide is often called a continental divide. For example, a lot of the Appalachian Trail is along the divide that separates the Mississippi Drainage Basin of the Midwest from the Eastern Drainage Basins. Another continental divide is found at the border between Minnesota and South Dakota. It's that little bump on the western side of Minnesota. It's the continental divide between water flowing up to Hudson Bay and water flowing southward to the Mississippi Delta. It's really unique in that the divide is the height of the road that passes between the two divides. It is without a doubt the most underwhelming continental divide in the United States. But Minnesotans enjoy and celebrating these things. Of course, the most famous divide is the Great Continental Divide, which separates the Atlantic and Arctic drainage basins from the Pacific Drainage Basin. So water that ends up in a river collects in a drainage basin. As I mentioned, it starts as rain in the headwaters. That is, along drainage divides. Runoff of precipitation occurs as sheet flow. Sheet flow is water in a thin layer flowing over the entire landscape. Very quickly, the water will begin to flow into very small channels called rills. What then happens is that rills join other rills. And with increasing amounts of water in the system, you get increasingly larger features. Rills join to make brooks. Brooks join to form creeks, and creeks join to form rivers. This is called the integration of drainage. And it all goes on within a river's drainage basin. As rivers flow into other rivers, frequently they flow into another drainage basin. For example, the Tennessee River flows out of its basin into the Ohio River basin when it joins the Ohio River. Then the Ohio River flows into the Mississippi River drainage basin. The Mississippi then flows to the Gulf of Mexico. As the integration of the drainage system occurs, the drainage basin gets larger and more complex, and frequently more water enters the river. That's how rivers form. But where do they end? Rivers will flow to what is called a base level. The ultimate base level is the ocean. You can also have local base levels. For example, the local base level of the Ohio River is the elevation of the Mississippi where it joins it. So that's how a river begins, develops, and ends. But how does that impact the landscape? As a river flows to its base, frequently there is a transition in geologic processes. In the headwaters, streams are frequently eroding and adding sediment to their load. Further down valley, streams will essentially be transporting their sediment load. Certainly, erosion does still occur, and more sediment is added to the system. But the predominant process is the transportation of sediment. Near its mouth, a stream deposits its sediment load. The reason for this is the changing characteristics of the flow of a river. In its headwaters, the river channel usually is steep. The word that's used is gradient, which refers to the amount of elevation that a stream changes in a given length of its channel. Further down valley, gradients decrease, streams get larger, and stream discharge increases. Finally, at river's mouth, the stream encounters standing water, the Gulf of Mexico in the case of the Mississippi. When this happens, the velocity of the stream changes markedly, and it no longer has the capability of transporting sediment. The result of a suddenly slowing down river is that you get deposition. When you understand those processes, much of the world becomes a fluvial laboratory that you can study. Let's take a look. There are really two types of rivers or streams. One is a braided stream, the other is a meandering stream. Braided streams are really beautiful, and geologically they're really interesting. You see braided streams in photos of the margins of glaciers, for example. The glaciers are melting and producing lots of water. At the same time, a glacier is depositing lots of sediment into that water. So frequently, at the terminus of a glacier, you have this condition where the streams that form from meltwater simply can't transport all the sediment that is generated by the glacier. Wherever braided streams form, it's a function of things like the volume of water in the stream, the sediment load, the stream velocity, and how readily eroded the material that make up the banks of the stream are. Braided streams can change into meandering streams further down the valley as flow characteristics change and sediment is deposited. Meandering streams are much more orderly in terms of stream processes and sediment accumulation. The meander is simply a bend in the river. It's the function of fluid being displaced perpendicular to flow. When a straight flowing stream encounters a rock or a tree has fallen into it, the water in the stream is deflected. This deflection, as a result of the conservation of angular momentum, will result in water accelerating around the curve. This is something everybody is aware of, but it's worth thinking about. Take a water balloon and swing it around in a circle. The shape of the water balloon will change as you accelerate the rate at which you spin it. Initially, the water balloon was close to round. As you spin it faster and faster, it becomes elongate. That's what also happens in a river. The water pushes outward and accelerates. This outward acceleration is what results in the process of stream meandering. Meandering drives both the sedimentary processes going on inside the river and the creation of the river landforms, the fluvial landscape. Sediment in a river consists of particles that are suspended. The wash load are particles that are transported without hitting the bottom of the stream. And the bed load are particles that are at the base of the stream, made up of sediment that is either rolling along or bouncing. Particles are not just being transported downstream. Because the motion of the stream is faster on the outside of the meander, river sediments end up traveling in a heliacal flow pattern that is frequently described as a corkscrew. As a result, sediments are being transported away from the outside high-velocity portion of a meander, called a cut bank, and they are being transported to the low-velocity inside of a meander, which is called a point bar. So as sediment moves toward one side and away from the other, over time, the river channel migrates. This is something that people who fish in rivers certainly have observed. The sediment piled up at a point bar makes an excellent place to enter into a river if you're going to be wading while you're fishing. Cut banks provide deep water and sometimes cooler water for fish to stay in. So someone fly fishing will often be in the shallow water of a point bar and dropping their fly over into the deep water of a cut bank. If you're in a boat, you'll notice this as well. Especially if the river is shallow, you'll find your boat moving towards the outer bend of the meander because not only is it deeper, but the water is moving faster. Mark Twain wrote about this happening to the old paddle wheelers traveling on the Mississippi River. In fact, that's where Samuel Clemens got his pen name, Mark Twain. The old paddle wheelers would travel from the outside of a meander on one side of the river to the outside of the meander on the other side of the river. What that meant was they had to cross through the center of the channel again and again. Because the river sediment was always being deposited and eroded, sandbars would also form in the middle of the channel. As the paddle wheeler made its way across the center part of the channel, the crew member would be up at the bow, measuring water depth with a rope line, crying out, "Mark Twain," when the water in the middle was deep enough to make the cross over. River pilot Samuel Clemens became author Mark Twain. A river is constantly changing. Mark Twain captured this in Life on the Mississippi, where he wrote, "The face of the water in time became a wonderful book, which told its mind to me without reserve, delivering its most cherished secrets as clearly as if it uttered them with a voice. And it was not a book to be read once and thrown aside, for it had a new story to tell every day." Over time, streams will continue to enlarge the meander pattern. With meander loops getting larger, the river taking a more circuitous route as it moves down the valley. Sometimes, usually during high flow events, a meandering river will excavate what's called a cutoff. The river, as a result of the erosion that occurs at high flow, creates a new and more efficient pathway. The meander is now cut off from the river's flow, and sometimes this results in the formation of a lake. This is called an oxbow lake because of its shape. The meandering process is one way the river ends up creating its own floodplain. A floodplain is defined as the flat portion of a river valley adjacent to or close by the deepest part of the valley. A river channel is created in this deepest part of the valley by erosion of the riverbed by the river. The floodplain is more of a depositional feature. As meanders migrate, point bar deposition lays down sands and gravels and very near an elevation to the river surface. That is the top of the channel. There's a second way floodplains are created, and this process is called overbank deposition, and it occurs during flood events. Overbank deposition occurs because river water that's carrying sediment slows down when the river water leaves its channel. It seems contradictory. You would think that a river in flood would be moving faster than it is in the channel, but that's no longer true after it leaves the channel. Think of it this way. Imagine a channel as a garden hose. You have water coming out of the hose at a certain velocity. Now lay down the hose. As the water flows beyond the channel of the hose and over the ground, you can see an abrupt decrease in water velocity. Why is that? The water is spreading out, and there's more friction generated because of more surface contact. The water is slower because it's being impeded. So as a river in flood exceeds its bank, the velocity of the water slows down, and the sediment is deposited on the floodplain. This is overbank deposition, and the suspended sediment load of the river is draped over the valley. The result is the formation of a flat, fine-grained deposit that covers the area surrounding rivers. And herein lies the dilemma. Floodplains are created during flooding. Due to increased rates of cutbank erosion and overbank deposition that occurred during floods. Geologists know that, yet floodplain materials are fine-grained sediments that are easily excavated or easily plowed. A floodplain is temptingly easy to build on. It's easy to farm, but there is no getting around it. Floodplains are formed by flooding. If you do build on a floodplain, or if you farm there, the buildings or the farm will be flooded. On average, most rivers in the United States flood every 2.3 years. Why build or use a floodplain if statistics say it's going to flood every 2.3 years? Please beware of building on a floodplain. So what does a floodplain look like? Look at the river and the area next to it. The land that is about the same elevation as the river is the floodplain. There's an oxbow lake, a good indication of a floodplain. Also, cleared land versus forest, small ponds and undrained lowlands, a floodplain is at an elevation just above the water table for much of the year. Finally, in this case, the absence of buildings. A natural question to ask is, what actually makes a river erode and deposit? I have already mentioned that faster water erodes and slower water deposits. So is it entirely stream velocity? The answer is almost. The best way to understand erosion, transport, and the deposition of sediment is by looking at the Holstrom diagram. In my classes, I like to spend a lot of time with the Holstrom diagram. It's one of these things that really helps students think about river processes. On one axis is stream velocity. On the other axis is sediment particle size. Plotted on the graphs are lines that indicate erosion velocity and settling velocity. Erosion velocity, frequently called critical erosion velocity, is the velocity of the river required to actually pick up a particle. On the right-hand side, you can see the velocities required for a river to move boulders. It's amazing. Depositional velocity is the flow rate of the stream that will result in a particle being deposited rather than transported. The area between critical erosion velocity and deposition velocity is the velocity of transport. So if you look at the diagram, there are two interesting relationships to observe. The first is that to erode clay, you have to have an erosion velocity similar to that of the velocity required to erode cobbles. How is that? It turns out that clay particles are flat and frequently their surfaces are ionically charged. The result is clay particles stay together and are difficult to erode. Throughout history, there are important lessons learned when formally trained engineers encounter earthen irrigation channels or canals and immediately assume they won't work because they're not armored with coarse sediment or cement. But the ancient canal builders knew what they were doing. Not only do clays make canal linings that are difficult to erode, the impermeable nature of clays also prevents water loss via infiltration into the canal floor. The other interesting thing about the Holstrom diagram is that if you look at the flow velocities required to deposit clay, you realize that essentially water has to be standing entirely still. This, of course, is the bane of lake enthusiasts. If clay gets into a lake system, it will stay suspended. As agricultural expansion has broken the prairie, soil clay particles have become increasingly mobile, both by wind transport and stream transport. In many areas, rivers are carrying clay into lakes or impoundments that clay simply doesn't settle out of. Suspended clay, of course, clouds up what was once a clear lake. A river deposits everything it carries once it reaches the presence of standing water, either a temporary base level or the ocean. This is the reason why deltas form at the edge of rivers. A stream meets either the ocean or a lake and deposits its sediment load. Over time, that pile of sediment builds further and further out into either the ocean or a lake, frequently in the triangle shape of a Greek letter delta. The Mississippi Delta has more of a bird foot form than the classic delta triangle form, but it has been collecting sediment from the Mississippi River for millions of years. The entire sedimentary package exceeds 25,000 feet. At the base of the Mississippi Delta, you have rock forming, both shale and sandstone, because of the overlying weight of the successively younger sediments. The same is true with the Amazon. Because of all the organics carried by both the Mississippi and the Amazon, those lowermost sedimentary rocks will soon develop natural gas reserves. This characteristic of dropping sediment in standing water essentially gives any reservoir along a river only a limited lifetime. All reservoirs created by a dam will eventually fill in with sediment. And that's happened, but most people aren't aware of it. The reality is, once you build a dam, you either have to live with a sediment-filled reservoir or keep dredging the sediment out of it. The Paonia Reservoir in Colorado is a pretty typical example of a dam whose reservoir infilled with sediment. Built in 1962, within 50 years it had pretty much filled to the point where the usefulness of the reservoir was over. Frequently, geologists use deltas to map the location of lakes that existed in the past. They are a very distinctive landform. Here's an example. This is a black and white photo of a delta landform that I think you'll be able to recognize. If you look on the left, there's a big looping valley, and on the right, a flat plain. Do you recognize the feature that seems to be spreading fingers over the plain? It's a delta with a meandering river leading up to it. In fact, it's a bird's foot delta, a lot like the Mississippi Delta. Do you see the patterns? The meander of the Mississippi River in the upper left and individual digits of the delta extending outward. But there's a difference, right? For one, the meander is in a deeply eroded valley, not like the Mississippi meandering across a floodplain. This is called an incised meander. At one point in time, the lake that created the mud-covered plain drained on the right side of the photo. When that happened, the river flowing into the lake rapidly downcut, incising the meander pattern. The draining of the basin also resulted in the exposure of the delta. You can see it all clearly, the delta apex, the individual digits of the bird's foot, and I think you can even see the old shorelines and point bars. But of course, you see more. You can see craters pockmarking the floor of the basin and the delta itself. These, of course, are impact craters, and the feature you're looking at is the Jezero crater delta on Mars. Jezero is a Slavic word for lake. This was the landing site of the 2020 Perseverance Mars rover mission. So once you know the landform, a delta is a delta is a delta, even on Mars. There are other landforms created by rivers that can be used to reconstruct the geologic history. The history of the Shenandoah River pirating the western portions of Gap Run and Goose Creek is in part known from the erosional valleys that were carved into Blue Ridge and later left abandoned. These valleys, Manassas Gap and Ashby Gap, are great examples of wind gaps, river valleys no longer occupied by rivers. Manassas Gap is the lowest pass in the Blue Ridge Mountains in Virginia and became an important thoroughfare for foot travelers and later railroads. These features are former river valleys. So why are they called wind gaps? They certainly weren't carved by wind. Legend has it that an early settler named Wint lived near Wind Gap in Pennsylvania. German settlers called it Wind's Gap, and that evolved into Wind Gap. Another river landform is a river terrace. These are former floodplains. They stand much higher than present river levels because they were deposited during past glaciations when river gradients were much steeper. River sediments from ancient rivers also can allow geologists to reconstruct the past. Remember Holstrom's diagram? Look at the velocity required to transport cobbles and boulders. Flow velocities of 300 centimeters per second or so. That's about 6 or 7 miles per hour. But look at this diagram. The largest particles in a river move as the bed load, where the particles are rolling and bouncing along the riverbed. Now look at the relative flow velocity on the right side of the diagram. Because of friction, flow velocity is much lower at the stream bed than in the middle of the stream. So think about it. These bedload particles are actually being moved by the slowest portion of the stream. I once crossed a river moving at that speed. It's faster than it sounds. I brought a small group of students on a hike to the Muldrow Glacier in Denali National Park in Alaska. Before we went, I checked in with the park rangers, and they told me that we would really need to bring a separate pair of shoes for river crossings. There were several crossings to make on this hike. I had never done this before. I'd always just taken off the hiking boots, waded barefoot, and then dried off and threw the boots back on. The extra shoes were in fact a necessity. That water was cold, fast-moving, and the cobbles that we were walking across were constantly in motion. It was crazy. Now look at this river sediment. This is the old riverbed of Glacial River Warren in the Minnesota River Valley. At one point in the history of Glacial Lake Agassiz, the southern outlet failed, sending a wall of water down the valley. These boulders represent the bedload of Glacial River Warren. It would have been an amazing thing to see. Understanding rivers combines an understanding of the landscape with an understanding of the hydrologic cycle. The geologic processes that occur in and around a river are the same processes that occurred in the geologic past. So observing present-day river landscapes and landforms also enables you to interpret the geologic record. You should visit a river at different times of the year and see it change for yourself. As the seasons change, the geologic processes change. To paraphrase something Heraclitus said, no one ever steps in the same river twice, for it's not the same river, and you're not the same person.